Now let's return to the pendulum examples where we have an equation of the form mx double prime plus gamma x prime plus ky equals 0. This is a harmonic oscillator with mass m, drag force gamma x double prime, which of course could be written as gamma times velocity v, and restoring force negative ky, and make these both negative because the drag force is in the direction opposite the velocity, the restoring force opposite the direction of the displacement from equilibrium, and we're using x here instead of y, and this restoring force is linear, being proportional to the first power of x. The nature of the solution depends on, of course, the initial conditions, but ultimately on the discriminant. Which is the square root of, well, the discriminant is not the square root, but I'll rescue myself and I'll say that the term in the quadratic formula, gamma squared minus 4km, implies discriminant gamma squared minus 4km. And the key is whether the discriminant is positive, negative, or 0. We've been over these cases previously, so I'm not going to detail the situation other than to say if the discriminant is positive, then we have two real solutions to the characteristic equation, which give us two exponential solutions. If the discriminant is 0, of course, we have repeated solutions, a case that we've just talked about. And if it's negative, then we're going to get an imaginary solution, an imaginary part to our solution. The square root of the negative discriminant is going to give us an imaginary number, and we'll use Euler's identity and we'll get oscillating solutions, sines and cosines. Typical solutions. We might get x of t equal some multiple of e to, let's say, the lambda 1t plus be to the lambda 2t, where lambda 1 and lambda 2 are two solutions of the characteristic equation. Lambda 1 and lambda 2 will usually be negative, and of course this type of solution will typically occur if you have a positive discriminant. Another solution, x of t, could have the form, I'll write it this way, e to the lambda t times a cosine of omega t plus b sine of omega t. Things are a little crowded here, sorry for that. Where omega is the square root of this is going to end up being k over m minus gamma squared over 4m squared. And we'll deal with that later. This simply comes out of the solution of the characteristic equation. This is going to be the coefficient of I when you have a negative discriminant. And another alternative form for this would be e to the lambda t times a cosine of the quantity omega t plus phi, where a and phi would be arbitrary constants as opposed to the arbitrary constants a and b here. And the phi depends on the relative magnitudes of a and b when you combine the cosine and the sine using basic trigonometric identities. In the case where gamma equals 0, omega is just the square root of k over m. And the real part of the solution is going to be 0. Now the lambda down here represents the real part of the solution, and we have to work through the algebra. I don't want to go through that right now. We're just trying to get an overview. And these are details that you have worked out or will work out. In any case, our solution will be either x of t equals a cosine omega t plus b sine omega t, or combining these using trigonometric identities, the form would be a cosine of omega t plus phi. And this would be a free oscillator with no damping. So it would be an oscillator that simply continues oscillating forever. We see that there's no decrease in the amplitude of this function, whereas down here the amplitude effectively becomes e to the lambda t times a, and again in this case lambda is typically negative. In fact, lambda is just negative gamma over 2m. The details of deriving these solutions are fairly straightforward once you have a little practice. So again, we're not going to solve the equations that give us these solutions. We've already done so in at least a few examples. What we want to do is we want to examine the nature of these solutions. We pretty much know where they come from, and with experience we'll have a better idea of where these solutions come from. But what is the nature of a solution that looks like this, as opposed to a solution that looks like this, or as opposed to a solution that looks like this or this?